Say it one more time.
Region, the plane that you work on, like the XY plane.
Yeah. So it's XY region normally. For right now, we're certainly doing a lot of Z equals F of XY, but it really is kind of arbitrary. But it's where we take the inputs that we're considering and for their outputs, right? So we draw these regions. Thank God they're in 2D, keeping in mind that the actual surface is hovering above it or below it, depending on what the output is. So now, for example, what do you say? Where are they at?
29 to 36.
29 to 36. Oh, where am I at? Oh, here we go. Okay, I got you. Blah, 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 blah. Well, let's try number 33. This would be a nice review of critical points and that. This one's not, well, it's a little bit interesting. We'll see. So one aspect of this, I don't know if you guys remember, again, you can always draw parallels between Math 180 and Math 281. 281, you just know it's going to be harder. 180, to find absolute maximum, you started finding the critical points, and then you also had to consider the endpoints. And then you can step back and just see who wins. This is basically the same idea, except now the idea of endpoints is going to become a little bit suckier, right? Just to use a technical term, because now my endpoints are going to be this definition of the boundary of this region. Shit. So, first thing I want you guys to do is just don't consider the boundary yet, obviously, because this is the part I got to talk about. Try to just define the critical points of this first. That's the part that you should be able to do right now. There we go, there we go. This is the part I try to make it a big deal, because it is a big deal, to realize that the critical points are going to be possibly the hardest part of the problem. Let me catch up to you guys. What do you get for fx? Pick your ass. For fy? Beautiful. Poor little 4 dude dies both times. Oh, trash. And now it's really up to you. I mean, if I try to start solving this one looks kind of nice. Try that. So I can of course factor it. Want to set equal to 0. So I get x equals 0 or y equals -1. Now here's the thing. Don't solve both sides, right? I've already got a required x and I got a required y. So now I just throw those values back in over there. Now I do the substitution. So x equals 0. What happens if x equals 0? And this has got to be equal to 0 here, right? If x equals 0, y has got to be 0. I don't have to write anything down. I love it. Or what if y is negative 1? Then I get negative 2 plus x squared equals 0. Plus or minus rad 2, I like it. All right, so what points do we have here then? If x equals 0, y equals 0. That's beautiful. So our critical points, 0, 0. Yeah, if y is negative 1, it leads to those two x values. So rad 2, negative 1. Negative rad 2, negative 1. That's the controlled way you construct your points. You don't just make a bunch of coordinates and then throw them all together. Like the right answer's got to be in there somewhere. And we're not going to, now hopefully you guys realize with what I said earlier, what are we not going to do with these that we normally would do for a local max or min question?
Do the second derivative?
Yeah, we don't have to do the second derivatives test, right? We just got to see who wins and who loses. So right now you can plug each one of these into the function and see what their outputs are. It's not enough though, because now we have to consider this is the domain, this is the region that we're working with. Right, this is the second part of the question. Second part of the setup, it gives you the function, but then it tells you the region in the xy plane you're working with. Take a second and see if you can't graph that. What's a better way to write this? Negative 1. Less or equal to x. So this one, of course, is. So those have to be true at the same time. I mean, those kind of basic things that if you don't know what to do, you're dead. There's no way you can do anything. But that's just a very basic idea. I don't mean to make you feel bad necessarily. You should feel a little bad. But if you can't draw the region, you can't do anything with it. So what does this look like? It's going to go negative 1, negative 1, no 1, negative 1. So it's going to be this big box here, right? Okay. So my boundaries are really well defined. This one is not the craziest one. If you had a triangle, then you'd probably have to figure out the equation of the line that goes between the 2 points. Ooh, you should be able to do that. This one's relatively nice because I know the equation of all the sides. What's the equation of let's call this one side 1. What's the equation of this side? Y equals 1. So if y equals 1, what does my function then become? On that boundary, which means, now again, let me make sure, let me take a step back for a second. I want to make sure everybody looks at this picture correctly. What is that point all about? I mean, don't tell me what that is. I didn't give you a good enough scale for it. But why is that point there, and what does it lead to? What does it mean for this problem? You want to tell me, what? This is a point that this problem allows me to use, right? Because it's in here. Like that point ain't got no output because it ain't allowed to be used. All right, so how would I use this point? Whatever it is. Let's say it's the point A, B. How would I use that point? What would I do with that point given the problem? I just plug it in. I mean, this is a function of a point in the xy plane. So given a point in the xy plane, it gives me an output parallel to the z-axis. Some of you guys are like, well, of course, but feels like not everybody really gets that. It's exactly the same idea as pick an x, plug it in, and you get an f of x. It tells you how high you are off the x-axis. Well, it's the same idea, except it tells you how high you are off the xy plane. Same exact idea. So when I draw this, this is a complete picture by any means, but it's just to make sure I can know that over this or underneath, depending on if z is positive or negative, that's where the actual surface is. I like it. So it's the same thing as if my function was as this from 1 to 3, and what we just drew would have been this. That's what we're looking at. That's the equivalence. That's the inputs I could use for that function, right? Do you guys see that? That's the inputs I would be able to use for that function. We're just not looking at the outputs. I can consider my y-axis even to be here. So we're doing the same thing. Now we're just drawing what inputs work. We didn't draw a damn thing about where they lead to. Okay. So with that in mind, if I do restrict myself to all the points on that boundary, then y has to be 1. X can, of course, be anything from what to what? Negative 1 to 1. All right, for this? And what does the function look like now? Yeah, so if y is 1, so I get y is 1, so I get 2x squared plus 5. I like it. Cool. And where's this guy going to have a maximum? And where's it going to have a minimum? Okay, this guy is now a parabola. Cool. And it's going to obviously have a minimum where? At the vertex, 11. It's an upward-facing parabola. I really want you guys to understand. The outputs to this, how does that relate to anything? If I pick an x, how does that output relate to anything? What does that output mean? Yes, it's the z. It's the z part. Of course it is. This is just specifically for the points that are on that boundary. I could plug any damn point I want to in that region, right? Any point. A, B, any point that's in there, I can plug it in. I'm picking all the points in that region where y is 1. Why did I do that? Because that's the equivalent of the endpoint for Math 180. That's the boundary. Then when I get this function, I actually am in 180. Or even, in this case, really 110 or 103. Just find the vertex. So I've got to find the max and the min for this function for these values of x. You got to do that for all 4 sides the same way. And then you compare them to the outputs you get for these. And the biggest one is the absolute max. And the smallest one is the absolute min. Yes, Jeff. So it's a harder problem. It is. It's a harder problem than the Math 180, but it is an easier problem than you might have thought it would be. So real quick, just to finish this out. Does anyone remember where's the maximum going to occur here? Or the minimum, sorry. The minimum.
0.
Yeah, at 0, right? So it's going to be 0, 5. So the minimum is going to occur, the minimum value, let's just put the value. The minimum value on this line, on that boundary, is 5. 5 is the value of what variable? Z. That's the output to this. So at 0, this thing will have a minimum. So when I plug a 0 in, the output is 5. That's the Z value. That's a contender. That's now a contestant in this absolute max and min weird-ass reality show. All right? What about the maximum? This might be, I don't know, this might be a little weird or not. Obviously, a maximum on this is going to have to appear at the endpoints. And they're both going to be a tie, aren't they? So when you plug a negative 1 in, you get 2 plus 5? 7. Okay. So now you would do this same thing I just did. You do it for each boundary, each wall. And then you plug these into that, and then you just stand back and see who won. Who won the max contest and who won the min contest. And you're done. So if it would have been like a triangle, that wall, you would have had to figure out the equation of the line connecting those points. You just got to figure out the line's equations. This one was relatively easy. I just had to realize that's that, and then I know all the equations of all 4 sides. I could plug that information in, get an easier function to work with. Beautiful. Maybe. So one more. What's this wall? Let's do this wall. X equals negative 1. So for this wall, what does the function look like? It's going to be 1 plus 4 is 5. right? Plus, well, it'll be y squared plus y, right? So it'll be y squared plus y plus 5. Another upward parabola, right? You guys see what's going on? And of course here, who remembers the shortcut to find the vertex? Complete the square. Or not even complete the square. That eventually leads to a quadratic formula, which eventually leads to negative b over 2a's in the middle of the quadratic formula output, so it must be where the vertex is because of symmetry. That's where the shortcut comes from. This will be, in this case, it'll be negative b over 2a equals y by meters. So what would this be? What's b?
1.
What's a? 1. So it'll be negative 1/2. You plug that in and see what the actual output is for that. Okay, maybe. You just repeat the process we did here for every side. Right. Just make sure you guys know. So when you plug this one in, what do you get? 4. So that already can't be a max, but it could be a min.
5.
You get 5 for that? And then this one, same thing?
Yeah.
So all the x's can't square here. So you got a bunch of 5s running around. They're not anything because they're in the middle of 4 and 7. 7 might be the max. That might be the min. Depends on what the other walls say. I like it. Maybe. And maybe.
So we have to repeat for the interval?
Yeah, so we just did 2 almost. You got to finish this one up. That's going to be where the min is, right? And then the max is going to be, you got to think about where the max might be for this. It's going to be at one of the endpoints. Why won't it be, and then you can just plug in both endpoints. I just really, why has it got to be one of the endpoints, and why is it not going to be a tie like the first one? Because this one is not. What was nice about this one? What was nice about this one? Where's the vertex? 0, yes. It's on the y-axis. So it was symmetric around its vertex. Here, this is not going to be, its vertex is shifted. But I still have to go between negative 1 and 1. It's not symmetric there. But who gives a shit? You just plug in the endpoints and see which one wins. Right? Again, the idea is always, where's the output maximum? Where's the output minimum? That's why it kind of really diminishes the amount of work I have to do at certain points. You just have to realize for each thing you're looking at, what's the easy way to do that, right? And some of you guys are going to do derivatives here, and all right, whatever. That'll work too, right? I mean, that's where we can prove x equals negative b over 2 using derivatives in 2 lines, right? Okay. Is that cool? Is that all right? Yeah. Anything else from homework stuff? I like it. Some of you guys are like, I have no idea where to start. Yes?
14.7, number 52.
Ooh, yeah, you gotta love these freaking boxes with no lids. Man. Please don't put a snake in there or something. So we got this here. Who wants it now? So I don't know if you remember what I told you. Something very simple to keep your mind focused is they're going to tell you something and they're going to ask you something. You write a formula for both of those things and see how they work together. So what do they tell me in 50? What was it again?
52.
52?
Yeah.
Oh, I was looking at theirs. All right, so the base of an aquarium with given volume is made of slate. And the side. Oh, I like this. So it's a cost problem. Okay. So the base of an aquarium with a given volume V is made up of slate, and the sides are made of glass. Slate costs 5 times as much as glass. Find the dimensions that minimize the cost. So right there, very first thing you got to be really careful about is, what function do I want to get to before I start taking partials? What function do I need to attack?
Cost.
The cost function, because that's the function, that's the thing I want to minimize. So if I said minimize the blank, you make a function for blank, because then you want to attack that. Don't make me a perimeter or a surface area or whatever. This is cost. That's going to be related to surface area, right? So you mean, I'm assuming it's going to be just a regular aquarium. I know the volume is V. So what are the sides? I would probably just call them
XZ and YZ.
Oh, I see what you mean. So this would be like X, Y, Z.
Yeah.
You could call it LWH, right? Doesn't really matter. So then you know that that X times Y times Z is V. That's what they tell me. And then they ask me about the cost. And I love what you just said. Per unit area, that's kind of the giveaway. So you got to find the surface area of this thing, which is really just find the area of several rectangles. So the one that's a different cost, let me see, the base is made of slate, and the sides are made of glass, which is good, because you want to be able to actually see the fish. It's probably a good idea. The whole reason you got to do it. So the base, of course, 5 times costly. Bless you. Damn. So the base is area
XY.
is XY. Now, how do I describe it? Doesn't matter how much this costs. It could be like an extra parameter, but does it say it matters how much that they actually cost? So I can set the cost, the base cost, be $1, or 1 unit of money, where the unit of money could be piles of $7. I don't know if you guys really understand. You could make a whole other variable that's not needed. It would be really silly, because since it doesn't matter, you can make it something easy. Some of you guys are like, what the shit is he talking about? But how much does the glass cost per unit area? I'm going to say it costs 1 something. Because the other thing costs 5 times as much. So on one level, it's going to, if you put another variable in there, it would just cancel. It would just divide out eventually. So the base cost, the cost of the base is going to be 5xy. And of course, I have these other sides. This side and the back side are going to be xz. And their cost will be xz because I just called it 1 what? 1 unit something. So that'd be x, where do you go? xz. And of course, this side and that side, same idea. Sorry, I got 2 of these.
YZ.
And I got 2 yz's. And they didn't say anything on the top. I'm going to assume that they were not considering the top. Just open. And this is going to be what? What the hell is this? No, it's not surface area because there's 5. That would be surface area. This is the cost function now. I love it. Isn't this the cost function?
Yeah.
And you could have put a little C for how much glass costs or whatever. And then slate would be 5 times C. But you see how once you start taking partial, setting equal to 0, C just freaking disappears anyway because it doesn't matter. Didn't say it mattered. Mathematically, it don't matter. So my physics people out there, it's just like maths very often. So this is going to be my cost function. It doesn't really matter what I call it. And then you just attack this like normal. You take CX, you take CY. Cool. Is that cool? I mean, I went actually a little further than I meant to, but I won't. The biggest problem people have with that is making the equation to work with in the first place. And that's not entirely everybody's fault. It's just that whoever was before, pre-calc is where they should hit you hard with this. 110 you get hit like this, pre-calc you should be hit like that. So you're ready for this, and you're ready for 180. Okay. So modeling a situation is that skill is disappearing. Yes.
Could you solve for Z in the volume equation?
Oh yeah, between these two. Yeah, so between these two, you got to use this information. We have one too many variables here.
So
I like it. So use this to help you with this. Cool. So that's why I always say, they tell you something, they ask you something, Use what they tell you in what they ask you. So then I don't have too many variables running around. Cool. And V, I know you got to be past the point that you care that they just said V. V is a number that I don't know. It's not a true variable, right? This is going to come for the ride. Yes, sure.
The same one. So I found the first partial for x.
Well, first of all, let's catch up here. So z equals v over xy. So then what do you get for cost? 5xy plus
2v over y.
yeah, 2v over y plus
2v over x.
2v over x. I like it. So when you plug that information in for z,
Yeah. And then the first, with respect to x, is 5y minus 2v over x squared.
yeah, like 2v over x squared.
And then, would you solve that for a y or for x?
I would solve it for y when you set equal to 0 because the x would require a rad.
Yeah.
It sort of depends on what the other one is. I mean, in this case, it's not going to help, but so if you have x squared in both, you can solve 1 for x squared and plug in directly for that. But if I have to take the radical more often than not, I don't want to go that route because that's plus or minus, and I don't want to deal with that shit. Right? Maybe. Cy, of course, would look very similar. Very similar. Yeah, there's a lot of symmetry there. So solve 1 for y, plug it in the other dude, set it equal, after you set equal to 0. This should be the part you can sink your teeth into. This is no real ambiguity except for not really understanding where things come from. I want to use this in this. Their system of equations. Okay. Anything else from homework stuff? Okay, cool. We left off with this guy. I think I talked about the changing the equations over. I hope you finished those. Let's just start from the beginning this time. And yeah, these you got to know. You just got to know these. If you don't already. So I mean, converting, I almost don't want to do this, but you just got to throw this stuff in here, right? So in this case, it's convert two rectangular coordinates. I have to give you some idea of what we're currently in. Because to be honest, that could be already rectangular. It's a weird way to show y, but y could be 5 pi over 3. So convert two rectangular means they're already in polar, which means I know what for this first one. R is 2, theta is 5 pi over 3. So what quadrant am I in?
4, 5. Yeah.
Fourth quadrant, right? I'm pi over 3 away from 2 pi, so I'm in the fourth quadrant. Okay, and now you just got to plug in, right? So, and the whole reason I said something about the fourth quadrant is you want to make sure that things come out correctly, but they should. Let's see, x would be 2 cosine, and what's the cosine of 5 pi over 3? Not negative though. We're in the fourth quadrant. Cosine is going to be positive, which is 1/2. So 1/2 times 2. It's amazing. You guys with me? So again, the picture would be I'm here at 5 pi over 3. Bam. Yeah. So of course the x piece is going to be positive. Pi over 3 is 60. The further I am away from the x-axis, the smaller cosine gets. So it's going to be the smaller value, which is 1/2. Not rad 3 over 2. All these things, hopefully you have that somehow in your brain. And y is going to be 2 times sine. Now sine is going to be positive or negative? Negative. And it's going to be the bigger one. Yeah, so it's going to be 2 times negative rad 3 over 2, so it's just going to be negative rad 3. So the point is going to be 1, negative rad 3. So that is the polar coordinate way to define the point that we know as this in the xy coordinate system. Okay, maybe. And then you just do the same thing. It's very repetitive. Here, what's going to happen, basically, what quadrant am I in for this guy? Third, because I'm a little over pi. I'm 1/6 pi over, right? So now the sine and cosine values we just had for part A are going to switch, and they're both going to be negative. Why are they going to switch? Because now I'm at a 30 reference instead of a 60. If you're having any trouble keeping up with what I'm saying, you have to go see somebody. Me, tutor, somebody. The trig's got to be right there, especially if we're getting a polar, it's going to be everywhere. Oh, shit. So then, let's see, we know R is that, theta is that. X is going to be negative 12 times cosine of that. Like we said, we're in the third quadrant, so they're both negative, right? What's cosine of 30? Yeah, it's close to the x-axis, so it's going to be the bigger option. So then I get x is 6 rad 3. And y is going to be negative 12 times the other guy. Negative 1/2. 6. So the point is 6 rad 3 comma 6. I like it, so please let that be nice. And you know x is arc cosine theta, and if only you weren't taught SOHCAHTOA, you would know that even better, because that would be the only thing you could go to. You just know it. So many more things are accessible when you think cosine likes x, sine likes y. We did these last time, but I'll just real quick, if you multiply both sides by r, and I know that r sine theta is y, and I know r squared is x squared plus y, so then I get this equation. And we talked about the fact that you can subtract this over, complete the square, you get a circle. And where would that circle, how would that circle move? Oh, it would start at the origin, which way would it move? Can anybody think ahead of which way it would move? Yeah, because it would end up being y minus something. So it's going to move up a little bit. So r equals 5 sine theta is a circle that's on the y-axis. So r equals something cosine theta would be a circle that's on the... Yeah, okay. It's crazy. Another situation close on the x, sine minus y. It's crazy. This one we did very quickly because we know that tangent theta is y over x. So if I take tangent of both sides, just take tangent of both sides. Tangent theta is y over x. What's tangent of pi over 6? Yeah, so we did this one last time, right? So then we get y equals square root of 3 over 3x. And again, tangent basically goes like sine because sine is the top. So wherever sine would be smaller, tangent's smaller. Wherever sine would be bigger, tangent's bigger. And where they're equal, it's 1. That's awesome. And then this guy we did, secant is actually
1 over cosine.
So then you multiply by cosine and you're there. Our cosine is x. I like it. Cool. All right, so that's what we did last time. Just want to go through it real quick. Yes?
So tangent is sine over cosine, so you can say that tangent is proportional to sine.
Exactly. Yes. So that's why you get a shortcut if you think about sine and cosine the way I do. All right. So how do I convert back? R is easy as hell. Right? How do I get R? R. Yeah, square root, in this case, it would be square root of 3 plus 1, so you get 2 for R. R is R squared is x squared plus y squared. That kicks ass. How do we get theta then? Yeah, so theta would be inverse tangent of? Yeah, y over x. And we just saw an example, and this is where you got to be really careful about quadrant, of course, because your output for theta is not necessarily going to be in the right quadrant. It's going to be a reference angle. Remember those days? Well, they're back. We just did one that had 1 over rad 3, right? It's got to be what reference angle? Yeah. And I'm supposed to be in the first quadrant, so there you go. Right? I'm supposed to be in the first quadrant. So theta is pi over 6. So I get 2 pi over 6. Don't ask me why they chose to do it r theta. It should have really been theta r. To be more like x, y, but oh well. We've gotten past it, I guess. This one's even easier, hopefully. What quadrant is that in, first off? Yeah, second quadrant here. And let's do the angle first. It would be the inverse tangent of negative 1.
So negative 5 forward part.
So it'd be pi over 4 reference angle, but I'm supposed to be in the second quadrant. 3 pi over 4. Yeah. I mean, it just takes like 5-10 seconds of thought just to realize where you're supposed to be. So I know the second part's going to be, what did I just say? 3 pi over 4. And then r is going to be easy, hopefully. Yeah, you get 2 fourths, 4 fourths square root 1. So r is 1. All right. So you guys, just take a minute. If you haven't done this yet, do these 3. Just remind you guys they're up here, what you need. It's really just plug and chug, but hopefully you can see if there's any simplifications you could do. Maybe I should show everybody this. So sketch the region, and then it would eventually lead to the limit. So what does the region look like? Sketch it. Oh, there. You know, we're going to do these there. You got one. Cool. 4, 5, 2.
English should be hard.
2, 4. Angles outside. Yeah. Cool. It's not impossible to have theta as a function of r, but it's very rare. You see what I'm saying? So that's why theta would most of the time be the outside interval. All right, let me catch up here. Right there. Really nothing gained by multiplying that x up yet. So y, of course, is our sine. 1 over our cosine. So when you multiply up, you get r squared sine theta cosine theta equals 1. Any identity that you can remember that would use? So if I double both sides, I can actually write this as
R squared.
Yeah, r squared,
Sine 2 theta equals 2.
and then you get like r squared equals 2, or just. And there's really no good reason to go further than that, to be honest. You do r equals plus or minus, but it doesn't make it look any better.
Is this the only way you can do it?
Not really.
You can do it.
Sure. How'd you do?
I did r squared equal secant theta over sin theta.
Oh, okay. All right. Sure. Yeah, same thing. I like it. Now this, of course, circle been shifted up. We saw an example of that already. But let's see if we can work it back. So what did you guys do? Anybody do something to this first or not?
R squared equals sine.
Yeah, you can just start plugging stuff in, sure, and then FOIL next. But you see how you get x squared plus y squared
Yeah.
if you FOIL it out first? So x squared plus y squared minus 4y plus 4 equals 1.
Is R squared
So you get r squared.
minus 4 R squared equal negative 3/3.
Yeah. So, I mean, it's no real good way to go from there, really. You can't really solve for r. You can see that? Okay? I mean, let's see. No, screw that. We don't do that. And then this guy, let me come over here. Hopefully this guy, you see something you do that. I'm always looking for the x squared plus y squared. It's so beautiful.
The Y squared.
Yeah, add y squared, so you got x squared plus y squared. Y over x squared plus y squared is r squared, y over x is tangent theta. That's more than likely a pretty funky thing. I mean, this one, can you solve it for y? Not easily. There's a way to solve it for y, do you guys know? It's just going to involve quadratic formula using x's as inputs for that. Yeah. But no, I don't want to do that. Right? So this would be a very funky graph, so it's good that we come up with something that kind of we know is going to be a pretty funky graph. Square root of tangent theta, basically, plus or minus. Don't forget your calculators are able to handle this. So we have R1 and R2, positive square root, negative square root tangent theta. You can actually see what the hell it's going to look like. So reacquaint yourself with the TI's polar graphing capability. That might be very handy. Here, have you guys done number 5 yet? If you haven't done that yet, try to do that real quick. And you can even sketch it right there if you do it lightly, because you're going to plot stuff over that. And just like we had, I suggested to you earlier this semester, do isometric paper, the 3D graph paper. Yeah, you want to get on with this bad thing. You get some polar graph paper for yourselves, please, dear God. If I see a lot of free-floating graphs or something, I'll just do a little butt graph for me. I want to see the points. I want to see them plotted. You know the one I'm talking about? The heart graph, whatever you want to call it. So depending on how you want to define your r-axis here, right? Of course the r-axis is everywhere, but I would normally call this 1, 2, 3, unless I have some freaky r's, and I don't, for later, right? So this would be r equals 1, r equals 2, r equals 3, r equals 4. So I've got to go from 2 to 4, but in between pi over 4 and pi over 2 for theta. So I want to go between these two, but from 2 to 4. So it's going to be r equals 1, r equals 2, from pi over 4 to pi over 2. And then I want to go out to r equal to 4. So we call this 1, 2, 3, 4. You guys cool with that? And then you can just... That's what we're about to get into, is hopefully you understand that the next step of this would be the region that we're integrating over. And they're going to give us a function to integrate. So it's going to be, you're going to love this. This is called a polar rectangle. Yeah. So if you're on curved, like if you had something on the surface of a balloon, if you drew something and then you blew it up, like a triangle, then you could have a triangle that has more than or less than 180 degrees, depending on which surface you're looking at, the inner or the outer. So there are other geometries. So this is a polar rectangle, and if I let r and theta get really small, which is of course what you're going to do when you're trying to build up an integral, if I wanted to integrate over this, I would break this into smaller and smaller and smaller parts. This does approach something with linear sides, right? Not curvy. So it actually does become a rectangle in the limit that I let r and theta go to 0. We're going to use that fact in a little while to figure out what the interval is going to look like. It's not what you might think. Okay, that's enough of that, Jeff. And then this, hopefully, I'm just going to go through this pretty quickly here. So there's a few different ways to do this, but the easiest way probably is to first look this way and then go out that much. There's another reason why it should really be flipped around, but oh well. So I want to look towards pi over 3, and then I want to go out 3. So I want to go out 1, 2, 3. There's 3 comma pi over 3. And I can figure out its rectangular coordinates just to check to see if it was in the right place, but I'm not going to do it. So 4, 3 pi over 2. Look towards 3 pi over 2. And then walk out 4. 1, 2, 3, 4. So this one, look towards pi. And then walk out 3.5. 1, 2, 3.5. Plop. I like it. So yeah, this is another situation where if you pick a good scale, that will help you a lot. So here I have, now I want to look towards negative pi over 6. So where's that going to be? Yeah, so it's just going to be, whoop. So that's why, if you can find this, I love this one where everything's labeled. This is a really good polar graph paper to have. There's 11 pi over 6, and I want to face in that direction, and I want to go 3/2, so 1.5. Look at your paper, Jeff. There you go. 1.5. Bam.
Are you using just 5?
Say again? Sorry?
Oh, never mind.
Oh, yes. Yeah, negative pi over 6. Here, I'm going to face 2 pi over 3, but then I'm actually going to go... Yeah, I'm going to go opposite for 2 pi over 3, so I'm going to end up going towards... Well, so it's going to have the same reference angle is another way to think of it, because it is kind of easy to lose the track, but I got to go towards 5 pi over 3, right? So then I'm going to look towards 2 pi over 3, and I'm going to go backwards 3 steps. So it'll be 1, 2, 3, bam. So r being negative just means you go back from where you're facing. Hopefully this is familiar. This is supposed to be just a quick review. And then here, bless you. Negative 11 pi over 12 is going to actually be what? 13 pi over 12. So that's the idea. There's actually an infinite number of ways to represent a point in polar, but just a few ways that actually aren't just repetitious. So negative 1 pi is here, and then I want to go 2 out. 1, 2. Shoo-bang. All right, and they're not meant to create something. Don't try to connect them together. All right, so obviously you should remember doing like r theta tables and making your graphs and doing like some weird-ass graphs that get spiral graph kind of stuff. One time I did the butterfly. You do a butterfly in your calculator. I don't know if you've ever seen that. The butterfly function, you should just look it up, plug the damn thing in your calculator, and it just makes a butterfly. If you give it enough range. Yeah, so look that up. Butterfly function. See what you get. All right. Okay, so the next level of this, of course, is going to be not just figuring out what region we're working over, but then setting up the integral. And the integral, one big problem with the integral that we have to figure out is it can't just be this. You can't. Because what we had before made complete sense. Why does this make complete sense? What does this really represent? dx dy represents a little element of area. Thank you. So this is really dA. If you're reading the book at all, you can see that's happening. And we also break up our plane into little area elements and then build little rectangular solids over them. That was the idea. And then sum those all up. That's where the big integral symbols come from, the double sum. So what's wrong then with this? It looks like it's the same idea, right? But hopefully, unit-wise, you see the problem. If x and y are both in feet, then sure enough, dx dy is square feet. It is in area. What's wrong with something here? The units on angles, of course, are going to be radians, but radians, hopefully you understand from what you've done with radians, they're sort of like placeholder units. They're not really true units in a sense that if I multiply, what's the arc length? You guys remember the formula for arc length?
Isn't that L?
Shoo, shoo. Here's S. Here's theta. Right? R theta. And I always looked at that as the formula, of course, you can develop why it is that. But on a unit level, it's like the R times theta gives it units. You can't say I've got to walk so many radians. It doesn't make really any sense. It's got to translate it into feet, meters. So when I multiply theta by R, it is giving it a length. So this is right now, this is currently just a DL. It's just a D length. Ain't good enough. We need a DA. We need area. Shit. So here's the thing. I'm not going to mimic the book's proof. You can look through the book's proof. It's a good proof. It's the hard proof. I could do all that up on the board, but you already got it in there. I'd rather show you sort of a more conceptual approach to the proof of what it's going to be. So the idea with this is I'm going to have some kind of area. Let's just say that I am working with something that looks like this. I'm going to have, it doesn't really matter. Let's work out. So I've got some sector that I'm working with, right? And it could be from, like we just did, from 2 to 4 for R. It could be some piece. But here's the main idea I've got to get. We're going to break this area down into little polar rectangles. So I'm going to zoom in. So like I would break this down. I'm going to zoom in on this. So now it's going to be like this. Right? I always think about a little piece of toast. Okay, now, when I go to do this integral, so what I'm doing is, I'm going to break this down into little rectangles. What would I consider next? So it's sort of like breaking down my x-axis into little intervals, and then building these rectangles up to the function, right? So what am I actually doing here? I'm going to build a little rectangular solid that goes up to z. It goes up to whatever this is. Okay, I like it. So that's the part we're not going to draw necessarily because it's kind of gross. We're focusing on the 2D, right? But the idea is I would build these things, and you can see in the book where they did the whole population of little rectangular solids, sum all those up, and of course you get the entire volume if you sum up all the little volume pieces. Same idea. But if I look at this, let me see you guys. So I'm going to, now this is already pretty tiny, but of course we're going to get here, I've got to let this get infinitesimally tiny. So let me not actually try to draw it. But in that limit, how far apart would these two be? Basically nothing, right? So what I'm going to get here is how wide would this side be? So let's see, this is going to be d theta here, right?
Yeah.
So how long is this side, actually?